weeks after homework, the last exam. So I think the last exam stopped at week 4. So maybe week 10 or so. If you have it up to that point, then that should be fine. I'll clarify that more next time or through email. Okay, so okay, yeah. So we were talking about orthogonal vectors, right? So again, we've generalized the definition to the not to the most abstract, but we generalized it enough to where we can now consider other spaces to be vector spaces, and then we define what it means to be a certain size and a certain direction, and then we define what it means to be orthogonal, right? Then we did orthogonal projections, meaning we projected a vector onto another vector, and we used the inner product to define it that way. And we looked at other space that we looked at inner products in other spaces for the set of continuous functions, right? The inner product there is the integral, right? So f times g dx from a to b. And we saw what it means to be orthogonal there. And then we went on to this section, which was we talked about basically what a set of an orthogonal set is, right? So every vector in my set has to be orthogonal. It has to be orthogonal, meaning the inner product between any two is 0, right? Which is what's here. And it's orthonormal if its inner product is 1 as well. Well, inner product with itself, which is the norm, right? So today, I'm gonna now give out some theorems and some results that are gonna be useful. Well, not useful, but it pretty much highlights why it's useful to have orthogonal and orthonormal vectors. So let's look at these. So this will be theorem. I guess it's going to be theorem 5.35. Okay. If S is the set, I guess, V1 all the way to Vn is an orthogonal set of non something just went wrong with my, so hold on, give it 1 second. Non-zero, have to be non-zero vectors in inner product. Then S is linearly independent. Okay, so big picture again, what is this saying? In an inner product space, if you have an inner product, right, vector space, and you see, and I give you this set right here, and you check that every vector has inner product 0 between each vector, right? Then that immediately implies that it's linearly independent, right? So you no longer have to check. Remember, if you're an Rn, you don't have to check the matrix. It's the matrix itself, and then RREF it down to the identity. If it's the identity, then it's linearly independent. You no longer have to do this. It's enough to show that everything is 0 with inner products. So this is actually one of the benefits of having an inner product space, and also orthogonal vectors, right? But what's more important is that the next thing, which is 5.32, is that now since you have this, if V is a inner product space, of dimension n, then any orthogonal set of n vectors is a basis for V, okay? Which is a vector space, right? So yeah, so week 5 to 10 is more likely, but I'll be more clear about that next time, or 3 now. Okay, so now if you have orthogonal vectors, not only do you have orthogonal vectors, but if you have a set of n orthogonal vectors and your vector space has dimension n, that set is also a basis. By the way, do you guys know what the dimension of a vector space is again? Huh? The what? Well, for vector spaces that have like R3, yes. But like in general, if I give you a vector space, how do you determine the dimension of it? Like, yeah, the number of basis elements, right? Yeah, exactly. Yeah, no, week 5, sorry, week 5 homework. Yeah, that's right. Week 5 homework isn't there. That was because I put it because that week we're supposed to have a test. So actually, if you want to know, I think I also did that for test 2. So if there's a skip in the week, that's basically where you have the exam. So anything before that is what you
Hello
should
there.
have. Yeah, so it should be
Hey,
6
what's
to
up?
9 then.
Hello, just hanging out at the moment.
Sweet.
I mean, the lecture
I'm gonna
notes.
change over to my
I
phone, so I'll
haven't
be right
figured out
back.
how to like download the actual
Because I'm
Sounds good.
recording
videos,
a class.
so
So.
no, I haven't uploaded
Gotcha.
the lecture videos itself. But the lecture notes I do give out. I send through email and remind at times. Okay. Perfect. So yeah, so the dimension of a vector space is just the number of basis elements. So now you can be sure about a set of orthogonal vectors. As long as it matches the dimension of the vector space, that is linear. That is a basis as well. Okay. So now comes the next thing. Okay. So clearly, if you've come across basis, I've given you a basis, and that basis might have been or might have not been a orthonormal basis, right? So how do I? So basically, the question becomes, how do I make a orthonormal basis, say B, from a given basis S, right? Well, the answer to this question that becomes it's you use something called Graham-Schmidt. Okay, so the process of going through getting a basis, if you have a basis, right, and I want an orthonormal basis, you use something called Graham-Schmidt. And honestly, it's not that hard. It's just you just follow some steps and then you're done. So here's the, I guess maybe I should just say the Graham process. Okay, so what do you do? Well, given B equals some basis elements, say V1, V2, all the way to Vn, right? For a vector space V. to obtain a orthonormal basis B prime, which we'll call now W1 all the way through Wn, right? You just do the same, you just do this. Pick a vector and your basis, denoted as as W1. It doesn't matter which one. I'm just picking V1. So just call that vector W1. Okay. So now our goal is then to find what W2, W3, W4, all the way to Wn is, right? So how do you do this? Well, to find W2, all you have to do is take V1 subtracted by, I guess you can say the projection of V2 onto W1. Okay. Okay, so let me actually take all this and put it over here because I'm gonna need more space. Okay, so that's your W2. That's your W2 here. I guess I should say more orthogonal. Oops. Okay, how do you get W3? Well, you take V1 subtracted from the projection. Sorry, you take V2 or V2. You take V. Why am I doing this? This should be V2 there, and this should be V3. So then you take the projection of V3 onto W1, and then subtract it by the projection of V3 or onto W3. So you see how each one of these depends on the previous steps. So here you pick one, right? This one depends on that first step. Then this one depends on that second step, and so on and so forth. So if you basically keep doing this until you get to Wn, which you can probably write it as yeah, it should be W2. I don't know why it's off day. Yeah, W2. And then this last one is Vn minus inner product of Vn, or sorry, the projection of Vn. So Vn onto W1 minus all the way to projection of Vn onto Wn minus 1. Okay, so all of this is like super maybe confusing. Like maybe this like has like I don't even know what to do if you give me a basis. And you're right, it probably is very it's probably way too much. But once you see an example worked out or one or two, it becomes very clear what it is. But anyway, so what does this process do? This process, so what this is then it makes B prime into is a orthogonal basis for B. So you can actually check it. You just take the inner product of any two any two would be 0. Okay, but if I'm looking for an orthonormal basis, what else do I have to do? So right now, are these are just orthogonal? That they're not orthonormal. What does it mean to be orthonormal? Oh, what? Yeah, exactly. Each one has to have norm 1, right? Or length 1. So we still have to do one other thing, which is then 3. Just let ui equal wi over the norm of wi. And once you do this, then say b prime prime, which is equal to the set of u1 all the way to un, is a orthonormal basis. And basically that's what you get, right? So remember, what we have a lot of advantages to wanting to do this, and I'll illustrate those here in a bit. But as of for right now, wanting to get an orthonormal basis is what we're looking for at the moment. Really, they don't have any. Okay, so let's see. So let's do an example. And this example was 5.32. So apply Schmidt to find a orthonormal to find an orthonormal basis for b is equal to 1, 1, 0, 1, 2, 0, 0, 1, 2, right? Okay. So right now this is a basis. I'm saying this is a basis. R2 or R3 rather. But it is not orthonormal, right? I mean, take the dot product between any two, it's not going to be 0, right? So this is what you do. Basically, we just follow these steps, right? So let W1 equal, say, 1, 1, 0. It doesn't matter which one you pick, just pick one, right? Then we find W2, which is going to be well, let's see. I should maybe label these as V1, V2, V3. Well, it's going to be, remember, it's going to be V2 minus the projection of V2 onto W1, right? Okay, so 1, 2, 0 minus, so remember the projection, so it's going to be the inner product of V2 with W1 over the norm of W1 times W1, right? So it's going to just be, what's the inner product in Rn? Yeah, dot product. So you're just going to take the dot product between V2 and W1. So 1, 2, 0 dotted with so 1, 2, 0 dot with W1, which is 1, 1, 0 divided by, well, the norm of 1, 1, 0, right? Well, what is this going to equal to? Well, if we do all the math or all the calculations, you should get negative 1/2, 1/2, 0. Okay. Okay, so now this is my W2. So now, how many more times do we need to do this? So if we're getting a basis for R3, how many basis elements do we need? 3. So you just need to do this 3 times, right? Or one more time after this. You just need W3. Next, for W3, so we have W3 minus is equal to, so it's going to be V3 minus the projection of V3 onto W1 minus the projection of V3 onto W2, right? Oh, that's just going to be, okay, so what's V3 here? 0, 1, 2 minus the projection of this. So it's going to be just 0, 1, 2 dotted with 1, 1, 0, right? Divided by the norm of 1, 1, 0 minus 0, 1, 2 dotted with, so W2 in this case was negative 1/2, 1/2, 0. Divided by the the norm of negative 1/2, 1/2, and 0. So if you put this in your calculator or whatever you want to use, what should come out is 0, 0, 2. Okay. So we have W1 is equal to 1, 1, 0. W2 is equal to negative 1/2 1/2 and 0, and W3 is equal to 0, 0, 2. Okay. So what should, okay, so according to what I just wrote, what should all 3 of these satisfy now? Right, big picture. Don't just like compute it and not know what you just did. What I mean, why did we do this again? They're orthogonal, right? So that means that if I take the dot product between any two, it should be 0, right? Well, I mean, just take the dot product between W1, W2. You get negative 1/2 plus 1/2 plus 0, which is definitely 0. W1 and W3, 1 times 0 is 0, 1 times 0 is 0, 0 times 2 is 0. Add them all up is 0. So these are indeed orthogonal now. So these are now these form an orthogonal basis for our vector space in R3. But we still need to do one more thing, right? Which is we need to normalize it, right? So next, we make them unit, right? So U1 is going to equal to W1 divided by the norm of W1, W2, W2, and then U3. Okay, so just if you do all these calculations, should be perfect. What you should get is for the first one, you should get square root of 2 over 2, square root of 2 over 2, and 0. This one, what you should get is negative square root of 2 over 2, square root of 2 over 2. Square root of 2 over 2 and 0. And then this last one, we should get 0, 0, 1. That's it. So B equals the vectors. Let's copy them. And so this is now a orthonormal basis. Okay. So, I mean, this is just the process of how you do it. I mean, there's no, it's literally just step by step. This is what you do, right? Now you can kind of see how if it's any more, it can get kind of have a, it can become a hassle, right? Because you're gonna have to like keep subtracting these like things off, right? And you're gonna have to compute like 10 dot products or like or 20 dot products if you have like a big basis. But nevertheless, it works, right? So usually what you do is you just have a computer do it, which is fine. But yeah, so okay. All right, so now we have this orthonormal basis, right? So why do we even care about all this stuff? Well, one thing is that is basically when we want to find coordinates towards for a vector in respect to a orthonormal basis, it's much easier if you were to do that as opposed to like just a normal basis. So what do I mean by that? This is what I mean. So I guess you can say a reason to do this have a orthonormal basis is that finding coordinates for a vector with respect to a orthonormal basis is much easier. So do you guys recall what it means to have a coordinate system with respect to another basis? So, I mean, if not, then I'll just say it. So basically, if you have a basis, like say, so just recall, so I mean, it's in the notes already, but I'll just repeat it. So if you have like a basis, say B, and all these are like V1 all the way to Vn, right? Then a vector X in a vector space has coordinates C1 through Cn if X is equal to C1 V1 Cn Vn. So basically the constants in the linear combination are the coordinates. So the coordinates would be C1 all the way to Cn. These will be the coordinates of that vector X with respect to the basis B in this case. So to find, but notice how, I mean, this, it'd be hard to find these. Even you have to solve for C1 through Cn, right? How would you even do that? Well, I mean, typically what you do in Rn is just set up your augmented matrix, RREF it, and solve for your C's, right? In other spaces like polynomials, you would have to like actually like gather every term with matching degrees and then equate the coefficients, and then you get another system, and then you find your C's, right? However, with orthonormal bases, you don't have to do this anymore. And and it's thanks to this theorem that I'm about to state. So theorem 5.3.3. So this is, I guess you can say, coordinates relative to an orthonormal basis. So if B is equal to, say, V1 all the way to Vn is an orthonormal basis in V, then the coordinate representation of, let's say, a vector W relative to, say, B is W is equal to W inner product with V1 all the way to W inner product with Vn. See, so here it's actually just given to you. Like literally, all you have to do is, as soon as I know what the vector is, whatever it has, and I know what, and since I'm given my vector W, and since I'm given my basis V1 through Vn, the only thing I need to know really is what the inner product is. As soon as I know that, I can compute each of these coefficients. So these are my C's now. So this is C1 and this is Cn. You don't have to go through the whole hassle of like having to do the RREF or like simplifying like giant polynomials down into getting a matrix system. You literally just compute the inner product between what you're given and those are the coordinates basically. Also, Pythagorean theorem holds in inner product spaces as well. That's another nice thing for you to have. So, okay, so let's see. So let's do a example that isn't, I guess, so straightforward. So let's just do one more. So example. So example 5.3. What did I say? 3. Find a orthonormal basis from in I guess the space of polynomials from the basis 1, x, and x squared. Okay. So again, you do the same thing, right? Let W equal 1, right? So then W2 is going to equal what? It's going to equal what's going to equal V2 minus the projection of V2 onto W1, which is just going to be, well, what's V2? It's going to be x minus the projection, minus the inner product of, so it's going to be V2, which is going to be x, and then 1 over inner product of 1 comma 1. So what's the inner product in the space of polynomials again? Yeah, the integral, right? So I guess I should say P2 on the interval -1 to 1, just to be so you have like limits of integration. Yeah, so this is going to equal x minus the integral of x dx -1 to 1 divided by the integral from -1 to 1 dx, right? So this is just going to equal x minus, well, you're going to get x squared over 2. Oh yeah, and then this should be v2. It should be w1, which is, well, the integral of that is just going to be 0, right? X is an odd function, and it's on a symmetric interval, so you don't have to calculate anything. And this is just going to be 2 down there times, so it's just going to be equal to what? X. So that's W2. And then W3. Well, what's it going to be? Well, it's going to be V3, which is x squared minus the inner product of x squared with W2, which was x. Oh, sorry, 1 over 1 times 1 minus inner product of x squared comma x over x, which is just going to be x squared minus the integral from -1 to 1 of x squared dx over integral of dx this times 1, doesn't matter. I guess this should be x right there. This would be x cubed, -1 to 1 over integral of x squared dx, -1 to 1 times x, right? Okay. Again, x cubed is an odd function on a symmetric interval. It's just going to be 0 here. So that's 0. So you don't have to worry about this thing anymore. If you integrate this, you're going to get 2/3 over 2 times 1, which is just going to give me x squared minus 1/3. So my orthonormal basis B is equal to orthogonal basis at least 1x x squared minus 1/3. Okay. And then we're not done yet. We have to make this norm. We have to have this length 1, right? Next, we normalize it, right? So how do you normalize it? Well, like this. Let U1 equal W1 over the norm of W1. U2 equal W2 over the norm of W2. And then U3 equal W3 over the norm of W3, right? So, I mean, W1 is 1, W2 is x, and okay, so on and so forth. So how do you, what's the norm in the space of polynomials? So remember, you don't ever have to memorize. You only have to memorize the inner product. So what is the norm in a general inner product space? It's the square root of the inner product of the vector with itself. Right. So this is just going to be, well, what is W1? It's just going to be 1 over the inner product, this, well, the square root of the inner product of 1 with itself, which is going to be 2, right? So it's just going to be 1 over square root of 2. This is going to be, W2 is x over the square root of x inner product with itself, which is the square root of the integral of x squared. So this should be just x over the square root of 2 over 3. Yeah, so that'd be, yeah. And then okay, perfect. So it would just be this then. So it would be the square root of 3 over 2. Yeah, we are. I'm just doing them in my head. Like, so I mean, I guess I shouldn't skip steps. Bad habit I have. So yeah, you're right. We are doing them. So I was just doing them all in my head. But yeah, you would have the square root of the integral from -1 to 1 of dx, which is just 1 over square root of 2, x over the square root of the integral of -1 to 1 of x squared dx, which should just be square root of 3 over 2 times x. And then this one is going to be, let's see, oh yeah, the ugly one. So x squared minus 1/3 over the square root of the integral from -1 to 1 of x squared minus 1/3 dx. Okay, so x cubed over 3 minus 1/3 x, -1 to -1. So one is, I think one of them is even, so one of them is odd. So you should have, so you have x cubed, so 1/3 minus 1/3 x. That should be, okay, should be 0. And then the other one should be should be 2/3. Okay, so whatever's down here, I'll let you guys calculate. I think, hold on, so I think it should be in here somewhere. Yeah, I guess, yeah, it's right there. Okay. So it should come out to be square root of square root of 5 over 2 square root of 2, 3x squared minus 1. But again, all you have to do is just calculate it. I didn't want to waste time trying to like figure out what the fractions were, but yeah, so these three now form an orthonormal basis. So B, I guess you can say with these three, square root of 3 over 2, and I guess you could say square root of 5 over 2 square root of 2, 3x squared minus 1 is a orthonormal basis for the space of polynomials of most degree 2. So yeah, so remember, so this might be, okay, so I guess I will probably ask something like this. I won't make it huge. I'll make probably 3 or less. I won't make it like 4. That'd be kind of unfair. If it's something I won't want to do, I'm not going to give it to you. So, yeah. So what? Right here. Yeah. So you consider them over whatever the interval they have there. It usually is noted as A to B. But whatever A and B is in that case, that's the ones you use. Every specified. Huh? Sorry. Yeah, it's gonna be. Yeah, you're not gonna like guess at it. No. Yeah. So all of that. I mean, it won't make sense if I just give you P2 and then knowing limits of integration. I have to give that to you for the question to make sense. So yeah. Okay. Any questions on this? I will probably give something like this, and I probably will make it not Rn. I probably will make it like the integral one. So practice that one. However, also keep in mind the conceptual stuff, right? Don't just not know what you're not doing, where you're doing. Don't just like be a robot and just do it and not know what you got at the end, because there will be true or false questions again. This time, I'll put less of them, but they're gonna be worth more since it'll be less of them, obviously. Okay. You don't even know that one because that's stupid. Okay, so next week, beginning Monday, and this weekend I'll have the review out for you sometime. So basically, I think that pretty much ends what I wanted to talk about, like inner product spaces in general. The next thing we'll do on Friday is we'll apply this to something called least square analysis. So basically, if you have like a plot of data, if you want to have the best fit line on there, you can use orthogonal projections, or all the stuff we just learned to derive what you call the normal equations. Which honestly, as soon as you know that, it's trivial at that point. But yeah, so we'll finish up with that, and then I guess that'll be the end of the material for the test. It's just gonna be 2 chapters at this point. Okay. See you guys later.